Cheng. I'm going to talk about my work, joint work with Ashwin Pananjady, who is sitting here, and also Martin Wainwright. So our work is on so-called permutation-based models, and the main contribution of our work is to break a 1/n barrier, which was observed in previous works. Okay, so let's start with the setup. So permutation-based models are particularly useful for an application called ranking from pairwise comparisons. In this setup, we have n items, and we observe a set of pairwise comparisons between the items. So here, the items are just a bunch of homeworks from students in, say, massive open online courses. So they are compared by their peers, and we would like to get a ranking of these homeworks from this set of pairwise comparisons. So what we observe is just a 0-1 binary matrix, and there's an underlying matrix of probabilities that govern this of this observed binary matrix. Namely, each entry is the probability of this Bernoulli random variable from the left. And the key assumption here is that when the items are ordered from the best to the worst, then the underlying matrix of probabilities is actually biased tonic, which means that it's monotone in both dimensions. This is a reasonable assumption because if you look at the first row of this matrix, it is a set of probabilities that the best item beats all the other items. And if you look at the second row, it's the second best item beats the probability is that the second best item beats the other items. So it's reasonable to assume that the first set of probabilities is larger than the second entry-wise. And also it's similar for the other dimensions. So we call this matrix biased tonic. So we start from this M, which is biased tonic. And because we don't know the ordering of the items, so we have an unknown permutation acting on the rows and columns of this matrix. And furthermore, we only observe a noisy sample of this matrix, which we call Y. And then our goal is to recover this permutation and the underlying matrix M. All right, so in fact, we allow different permutations on the rows and matrix and the columns of the matrix, which we call pi and sigma, because this allows us to study applications like crowd labeling and graph-on estimation. So our goal is to get a triplet of estimators, where in particular this estimator for M is biased tonic, and we want to make the risk in the squared Frobenius error small. Okay. And previously, so if we study this normalized risk, which is normalized by 1/n squared, then previously Shah et al. Established the minimized risk, which is at 1/n. However, all the polynomial-time algorithms only achieve a rate 1/√n. So for example, the first two methods are spectral, so that's where suboptimality usually kicks in. In fact, this 1/√n is optimal if the estimator is required to be adaptive in a certain sense. But we are more interested in this global risk. And in fact, our main contribution here is to show that we can get a rate n to the -3/4. So we can break the 1/√n barrier in polytime. Although it's not optimal yet, but it's much faster than the previous rates achieved. Okay, so now if we study this unnormalized risk, then we are just aiming at the rate n to the 5/4. So how can we do this? So the meta algorithm consists of two steps. The first step is just to find the permutations, pi hat and sigma hat. And the second step is, say we think of these two permutations as a true permutation, and we do a least squares to find the matrix M. And because the set of biased tonic matrices is convex, this problem can be solved efficiently. And moreover, it only incurs an error of size n in the unnormalized risk, which is smaller than what we are looking for. So in fact, all the hardness of the problem lies in the first step, which is to find the permutations. Let's just focus on finding the row permutation because the column one is completely analogous. So how can we sort the rows of this noisy matrix Y? This first idea, very simple. So is to just sum along the rows and then sort the row sums. But the problem of this approach is that the deviation of a row sum is at root n, and this incurs an error root n for every row. And combining all the rows, we get a rate n to the 3/2. So there's a root n gap here. This was observed in previous works. How can we improve this? So let's assume that the columns are correctly ordered. So there's Oracle giving us this order now. What we can do is that, say we have a bunch of rows which are not distinguished by row sums. What we can do is to zoom in into a small block here and study partial row sums on that block. And this final information will help us achieve a faster rate. And in fact, if we just block the columns into root n blocks, each of size root n, and if we combine all the partial row sums here, because the deviation of a partial row sum is only root n, which is n to the 1/4, so we can show that this incurs an error only n to the 1/4 for each row, and summing over the n rows, we will get n to the 5/4. But the problem is that in reality, we don't have this oracle giving us the order of the columns. So what we can do is to first sort the columns by the column sums, and then partition the columns also by the column sums. So the deviation of a column sum is root n. So if we partition the columns into root n blocks, then what we can guarantee is that at the block level, the columns are approximately sorted. So our algorithm from the previous slides can still be applied here. Although there are some technical issues that forbids us to prove a row-wise error of n to the 1/4 for when the columns are not correctly sorted, but fortunately, we can still get the rate n to the 5/4 for the whole matrix. And that's how we improve the previous rates. All right, so let me end with a few future directions. So first, you might wonder, can we iterate this procedure to get finer and finer estimates? But unfortunately, that's not the case. We have a counterexample for which even a multi-stage algorithm doesn't improve the rate. So either you should look for some global algorithm that takes advantage of other information other than the partial row sums, or maybe there's a statistical computational gap. Also, this rate n to the 1/4 is essential in another metric, and you're welcome to stop by our poster for that. And finally, there are many open questions. For example, if we sample the pairwise comparisons according to a fixed graph instead of uniformly randomly, as we did in the paper, what's the rate? And how about models for partial orders? And also, there are also observed this root n gap in other average case permutation-based models. So if you're interested in computational statistical gaps, you should definitely look at one of those models. All right, thank you.
One quick question while the last speaker gets ready. Yes, no?
Yeah,
yes, over there.
Yes.
So I must be missing something. Why doesn't this conflict with the
Oh, because so this lower bound based on Planck-Clique, this study is estimated that is required to be adaptive to the block structure. So this in fact this lower bound is based on something called the adaptivity index, which is studied in that paper, but we study the global risk. So our estimator doesn't really adapt to the block structure of the matrix. So yeah, in fact, in general, the bi-isotonic matrix does not have to be a block matrix. We can discuss more of that offline. Yeah.
Thank you. Thanks. Yeah. And the last speaker.